Welcome back to EGME-333 Fluid Mechanics. This video will continue discussing the Reynolds Transport Theorem, but will primarily focus on evaluating the scalar product in the control surface integral that is found within the Reynolds Transport Theorem equation. So when we are discussing the evaluation of the scalar product, we are specifically referring to the velocity field dotted with the unit normal vector v dot n. So when we look at the Reynolds Transport Theorem, it contains a surface integral in its expression that accounts for the net outflow of the parameter rho lowercase b across the control surface. So the question then becomes, how do we evaluate this scalar product, v dot n? In general, if we look at a control surface, each point in the control surface consists of a local unit vector little n that always points away from the control surface and is oriented perpendicular or normal to the control surface. Again, the normal unit vector, bold little n, always points away from the control volume. Across the control surface, there could always exist some velocity vector, bold capital V, where its orientation does not necessarily have to match that of the unit normal. In fact, in general, we assume that there does exist an angle theta between the unit vector little n and the velocity vector capital bold V. So in general, v dot n should equal the magnitude of the velocity or the speed capital V times the cosine of the angle between the velocity vector and the unit normal vector little bold n. However, I do want to discuss three specific cases where we can categorize v dot n. The first case we want to consider is when the velocity vector is parallel to the unit vector. In this case is what we refer to as an outlet. The reason for that is because the product of v dot n will be a positive quantity. Recall that the dot product between two vectors leads to a scalar quantity, so direction doesn't matter. But for this specific case, whether a quantity is positive, to us that indicates that it represents an outlet, meaning that fluxes of mass, momentum, and energy are exiting our control volume through the control surface. The second case is when the velocity vector is pointing in the opposite direction of the unit vector. And this situation is what we call an inlet, where v dot n is going to lead to a negative quantity. So in essence, the fluxes of mass, momentum, and energy are entering our control volume through the control surface. Now, there is this special case where the velocity vector, bold capital V, happens to be perpendicular or tangential to the unit normal vector, bold little n. In this case is what we call a barrier, where the product of v dot n is mathematically equal to 0. Recall that in vector calculus, whenever we have two perpendicular vectors, their dot product is automatically equal to 0. And in this case, we can imagine that locally, the velocity field is traveling parallel or tangential to the local control surface. So in essence, the flow is neither entering or exiting the control surface, but rather traveling around the control surface, along the control surface. We often see this around solid boundaries where the flow is traveling parallel to a solid boundary versus traversing or crossing that boundary. However, mathematically, in this situation, V dot n is mathematically equal to 0, and this portion of the control surface does not contribute into the evaluation of the control surface integral. Now, given that we are discussing this particular integral that quantifies the net flux going into or out of the control volume, I do want to discuss a special case or a particular assumption that we often make when analyzing fluid flows. And that is the assumption of one-dimensional inlets and outlets. Now, in many applications, the flow across a control surface only occurs at specific inlets and outlets. For example, let's imagine the flow exiting through a water hose. In this specific example, the water within the hose is only exiting the hose within a specific outlet. In addition, it may have a variable velocity profile at the exit. However, often we can argue that this velocity profile can be approximated as uniform across the entire cross-sectional area, whether it's an inlet or an outlet. And instead of working with this variable velocity field, we can instead simply approximate it as a one-dimensional velocity field. To do that, we would essentially consider the mass flow rate m dot divided by the density of the fluid times its cross-sectional area. So if we make this assumption of one-dimensional inlets and outlets, we can essentially simplify our control surface integral to simply a sum of inlets and outlets, where we can take the control surface integral and transform that into the summation of all of the outlet flux minus all of the inlet flux. I'll remind you that V dot n will dictate whether or not a particular surface within the control surface should be treated as either an inlet or an outlet. And that depends on the orientation of the local velocity vector relative to the local unit normal. So we can simplify this expression as simply just the summation of all the outlet flux, m dot times b sub I, minus the summation of all of the inlet fluxes, m sub I times b sub I, going into the control volume. To illustrate how to utilize the one-dimensional inlets and outlets assumption, let's consider the following flow through this particular pipe system. So to apply the one-dimensional inlets and outlets, I would argue that it's always important to first draw your control volume by specifying the corresponding control surface, illustrated here by the dashed red line. Then, at each point where flow is either entering or exiting the system, go ahead and sketch the corresponding local unit vector. Now I'll highlight that the unit vector always points away from the control surface as shown here at point 1. Similarly at point 2, the control surface is pointing away, point 3, point 4, point 5, and point 6. The orientation of the unit vector bold little n is independent of the local velocity vector. it is simply dependent on the shape of the control volume. But at each of these 6 points of interest, we want to sketch the local unit vector. So if we go through point by point, we can then specify what are considered inlets and what are considered outlets so that we can expand out the one-dimensional inlets and outlets assumption. So if we look at point 1 highlighted in red, we can see that the local velocity vector v sub 1 is pointing in the opposite direction of the local unit vector. Therefore, at point 1, this would be considered an inlet. So we can start expanding out the control surface integral to say it is equal to negative rho 1 v1 a1 b sub 1. Given that I've only looked at 1 point in my entire control volume, I'm not done yet. I still have to go through the 5 remaining points of interest. When we look at point 2, in a similar fashion, we see that the local velocity vector v sub 2 is pointing in the opposite direction of the local unit vector little n. So just as it was the case in point 1, at point 2, we can then conclude that this corresponds to an inlet. So we can subtract rho 2 times v2 times a2 times b sub 2. Moving on to point 3, in this case we see the opposite, where the local velocity, capital V sub 3, happens to be pointing in the same direction as the local unit vector little n. Therefore, we can conclude that local surface, surface 3, corresponds to an outlet. Therefore, we want to add the product of rho 3 times capital V sub 3 times a sub 3 times b sub 3. If we look at point 4, we see the same thing. The local velocity vector points away from the control surface and happens to be pointing in the same direction as a local unit vector. Therefore, point 4 also corresponds to an outlet. So we add rho sub 4 times v sub 4 times a sub 4 times b sub 4. Point 5, same situation. The local velocity points away from the control surface and it points in the same direction as a local unit vector. So we add that quantity or that flux to the entire integral. And this, lastly, when we look at point 6, we see the exact same thing, where the local velocity vector v sub x points in the same direction as a little unit vector, little bold little n. So we add rho sub 6 times capital V sub 6 times capital A sub 6 times lowercase b sub 6. And in this fashion, by utilizing the one-dimensional inlets and outlets assumption, we've taken a control surface integral and approximated it by a sum of the difference between outlets minus the sum of all of the inlets.